Trigonometric integrals. In this section, we're going to use trig identities that we learned from our trig course to integrate certain combinations of trig functions. We're going to start with powers of sine and cosine. Let's talk about the following example. Evaluate the primitive of this integrand, which is a power of cosine. So cosine cubed dx. If you try to simply substitute u for cosine, if you start by just doing a regular u substitution by setting u to be cosine, as such, du would be negative sine x dx. So, and we don't have the sine, so this might be not helpful in order to integrate the power of cosine. Okay, so we would like to actually have an extra factor of sine to be able to integrate. Okay, so similarly, if you have a power of sine, you're going to also require to have an extra cosine factor in order to integrate. So what we're going to do here is we're going to separate a cosine factor, and if you do so, you're going to be left with cosine squared x, and you can link cosine squared to sine via the Pythagorean identity, right? The sine squared x plus cosine squared x equals 1. Okay, so let's see how it's gonna go. So let me just erase this part. So I can rewrite this as cosine squared x times cosine x and cosine squared x by the Pythagorean identity, right? So by the Pythagorean identity, we can rewrite it as 1 minus sine squared x. Okay, so remember the Pythagorean identity is cosine squared x plus sine squared x equals 1. So cosine squared is 1 minus sine squared, and as such we can rewrite cosine squared as this. So we obtain 1 minus sine squared x times cosine x, correct? So we rewrote this guy, cosine squared, via this identity as 1 minus sine squared. As such, now if you set u to be sine, then you're gonna have its derivative that's gonna have to do with cosine, which is already existing here. Okay, so we set the stage for a good u substitution to actually be helpful. All right, and as such, what do we obtain? So as such, we obtain the following. So therefore, this integral, the given one, is equal to this integral, 1 minus sine squared x times cosine x dx, right? Because we said that cosine cube x is equal to this product. So we got this. And then we can use an appropriate u substitution. Namely, I can say let u be sine x, right? So let u be sine x, and as such du becomes cosine x dx. Agree with this? So this would be a good u substitution because cosine is there. Okay, so we get that, and then you may rewrite this integral as 1 minus, remember this means the square of sine x, and if sine x is u, this becomes the square of u. So the square of u, or u squared, times cosine x dx. Cosine x dx, this guy is du, correct? So this guy is du. So instead of having cosine x dx, I can write du. Okay, so times du. Okay, and now you're integrating a polynomial, so that's easy. So this is equal to primitive of 1 du is u, minus primitive of u squared du is u cubed over 3, right? Plus a constant of integration. And this is equal to, remember what u is, we need to give the answer in terms of x because the integral is in terms of x. So u happen to be sine x, that's our choice. So sine x minus u cube is sine cube x over 3, right? Plus plus c, again, where c is an arbitrary real number. Correct? Okay. So in general, we try to write an integrand like this involving powers of sine and cosine in a form where we have only one cosine factor, like here, one cosine factor, and the remainder of the expression is going to be in terms of sine. Okay, and then we set u to be sine x, and then du becomes cosine x dx. Okay. In parallel, also, if we have powers of sine, we can have only one of the sine factors. So instead of cosine, we're gonna pull out a sine, and the remainder of the expression is gonna be in terms of cosine, and then we set u to be cosine, and du becomes the sine or the negative sine x dx. Okay. And then the identity, the Pythagorean identity, is gonna allow us to convert back and forth between the even powers of sine and cosine. Okay. Let's do another example. So let's call it example 2. And let's try to evaluate now this integral. Sine to power 5x times cosine squared x dx. Okay. So you may think, okay, let me rewrite cosine squared in terms of sine squared by using the Pythagorean identity, right? So if you rewrite this in terms of sine squared, this becomes 1 minus sine squared, and the whole expression becomes just in terms of sine. And as such, we cannot play the u substitution game anymore because you don't have an extra cosine factor involved. Instead, what I'm gonna do, I'm gonna do exactly play the same game as I did above. I'm gonna isolate a single sine here by itself. That's gonna give me sine to power 4x, and that expression sine to power 4x, which is the square of sine squared. Then I'm gonna invoke the Pythagorean identity to actually write that expression in terms of cosine. Okay, so let me give you the details now. So I'm gonna write this whole thing. Actually, let me just focus on this. I'm gonna write this thing as sine to power 4x times sine x. Okay, and this guy, raising something to power 4 is the same thing as raising the square of the raising the square to the square, right? So which means sine squared x to power 2. Remember, this such an exponential expression, you multiply the powers here. 2 times 2 is 4, correct? Times this sine x. Okay, now you invoke the Pythagorean identity that we just recalled above. Let's do it again. So the Pythagorean identity, and what do you get? You know that as such, sine squared x is 1 minus cosine squared x. Okay, so you can rewrite sine squared x as 1 minus cosine squared x. So this becomes in terms of cosine, this is in terms of cosine, and if you set now the u to be cosine, the differential of u would be negative sine x dx. Okay, so Okay, so let's write that. This is then equal to 1 minus cosine squared x squared times sine x. Okay, and let me be very clear here. This is the guy, that's the guy that got replaced by this thing. Okay, all right. So therefore, this integral that we have, how about we give it a name? How about the name I? So therefore, I is simply the primitive of this expression, which now can be seen as this. So 1 minus cosine squared x squared times sine x, that's this guy, times the square of cosine, okay, dx. And as I said, now you can label cosine x as u, and the du becomes something that has to do with sine x dx. Okay, so let's be specific. If you introduce the letter u to be cosine x, this means, or this entails, that du is minus sine x dx. Correct? Okay, and as such, I becomes the primitive of, this becomes 1 minus the square of cosine is the square of u now, square times sine x dx. So let me just circle this part. Sine x dx, sine x dx is negative du, right? So this is negative du, correct? Just look at it here. So sine x dx, this part is negative du. Okay, all right, and then so this is negative du. Let me pull the negative outside, du. And cosine squared, well, cosine is u, so this becomes u squared, correct? So we get so we are integrating a polynomial now, right? So how would you integrate this thing? How about performing the square here and then multiplying that result by u squared? Okay, so it becomes a simple polynomial, and this polynomial is in terms of u, which is the variable of that integral, right? Okay, so minus primitive of, let's square this difference. So it's 1 minus 2 u squared plus u to power 4, that's this guy, times the square of u du. And now let's distribute this multiplication over addition and subtraction inside. We obtain minus the primitive of u squared times 1 is u squared. U squared times negative 2 u squared is negative 2 to power u to power 4. I added the powers. I didn't multiply, even though 2 times 2 is still 2 plus 2. But I added in this case. Plus u to power 4 times u to power 2 is u to power 6, right? du. Okay, so that's the polynomial I was alluding to earlier. And now it's a simple integration. And this is minus u cubed over 3 plus, because minus times the minus is plus, 2 over 5 u to power 5, minus times plus is minus, u to power 7 over 7, right? Plus a constant of integration, let's call it c. Now back to what u means to the problem. U means cosine x, so that becomes negative 1/3 cosine cube x plus 2/5 cosine to power 5x minus 1 over 7 cosine to power 7x plus c, where c is an arbitrary constant. Okay. So in these two examples that we just finished, in each of them, in this one and this one, the integrand had an odd power of sine or cosine, and that which enabled us to separate a single factor, right? In this case, we separated a single factor of cosine because the power of cosine happened to be 3, which is odd, and in this case the power of sine was odd, so we isolated a sine, a single factor of sine, correct? Now if the integrand contains only even powers of both sine and cosine, then what we just did in examples 1 and 2 fails. So that strategy fails. In this scenario, we're gonna use half-angle identities that we learned in trig courses. So let me remind you of that. So recall the following half-angle identities. Okay. So half-angle identities, those are identities which connect half the angle to the angle, right? So sine squared of theta is equal to half 1 minus cosine twice theta, right? So this is one of the half-angle identities, and cosine squared of theta is equal to half times 1 plus cosine twice of theta. Okay, so we use these whenever we don't have odd power of sine and we don't have odd power of cosine in the integrand. Let's see an example. Let's consider the following. Let's evaluate this definite integral that's defined between 0 and pi, where the integrand is sine squared x dx. So observe here, if you simply replace sine squared x by 1 minus cosine squared, in other words, if you simply use the Pythagorean identity, the new integral is going to be just as hard as the given one. Okay. So instead, what I'm going to do, I'm going to employ the half-angle identity over here that's going to linearize this power. Instead of having a square, it's going to linearize it. In other words, the power is going to become a 1. Okay. And let's see what we obtain. So that's going to be then. So again, I'm going to replace this entity here, this integrand, by 1/2 1 minus cosine twice x in this case, right? So x. And why? What is this coming from? It's coming from the half-angle identity. So how about we label that as asterisk? So this is simply by asterisk. Okay. All right, and then this integral becomes, so this definite integral now becomes equal to the definite integral from 0 to pi half 1 minus cosine twice x dx. Okay. All right, and this is an easy integral because cosine, now I have a linear power for cosine, so this is technically equal to half times, let's split the integral, so integral from 0 to pi 1 dx, so dx, right, remember this means 1 dx, minus the integral from 0 to pi cosine 2x dx. Okay. The first one is immediate. What is that one? Let's do it over here. So what's this one? This is simply the primitive function is just x, right? And if you take x between pi and 0, this is simply pi. Am I correct on this? So that's pi. And the other one is not hard, but a little harder than the first one. Okay, so this one here, what I can do is I can use a u substitution for this guy. So I can label 2x as u, right? So let's do that. So I can let u to be 2x, and this means that du becomes twice dx, which means half du is dx, right? Agree with that? So that's what's gonna be used actually to evaluate this. I'm using u substitution for this integral, and 2x I'm labeling it as u. Okay, so let me move all of this a little here. Okay, and let's go back to evaluate this integral. So this is where that thing is used, right? It's right there. Okay, and as such I get that this is the integral of cosine of 2x, which is now u, and dx is half du, so I get half du. And now what are the bounds of u? If x is at 0, u is also at 0. And if x goes to pi, u is gonna go to 2 pi, right? Because the u is twice the x. If x is at pi, u is gonna be twice that, which is 2 pi. Okay? So again, this integral is equal to that, right? Very good. And then this is what? What's the primitive of cosine of u? Primitive of cosine of u is sine of u, right? So we get sine of u, but u is now between 2 pi and 0, so sine of 2 pi minus sine of 0. Correct? Okay. And this is 0. Why? Because sine of 2 pi is 0 and sine of 0 is 0, so this whole thing is 0. Make sense? Okay. So this whole thing is 0 then. So the answer is simply half pi. Okay. So the answer is simply half pi. Why it's half pi? Because that guy happened to be 0, and this is pi, and there's a half outside, so it becomes half the pi, which is 1 over 2 pi. Okay, so what does this represent geometrically? This represents, you have a function sine squared x, which is a non-negative entity, right? A non-negative function. And the region that's bounded between the function, the x-axis, and the two vertical lines 0 and pi, x equals 0 and x equals pi, has this area, right? This is the net area of that function. So of that area. This is the net area of the region bounded by the function sine squared x from above, the x-axis from below, and the two vertical lines x equals 0 and x equals pi. Alright? Okay, so do you have another way to actually evaluate this guy? Can you come up with another way to evaluate this guy? So another approach. I'm gonna give you direction on how to do it and try to complete it on your own. Obviously ask me if you cannot. So another approach, make use of the reduction formula. The reduction formula given in the earlier section, which was integration by parts section. Okay, So make use of the reduction formula given in the integration by part section, which at the time connected any even power. If you want to integrate an even power of a sine function, you can connect it all the way by repeated application of that reduction formula. You can link it all the way to the integral of 1 dx. Correct? We talked about it in that. Just quickly, we talked about it in that video, but we also talked about it in class. Okay. All right. So this would be another approach. All right. So let's move on to another one. Let's call it example 4. And let's take the following integral. So let's find the indefinite integral of sine to power 4x dx. Okay. So what I'm gonna say here is this is very similar to the discussion we just made above, right? This is of the form sine to power even power. And the reduction formula we can still apply it. Correct? So I'm gonna let you do this approach number 1. So approach number 1 is by making use of the reduction formula. So ask me in class if you're not successful in using it. So here I meant you make use of the reduction formula. So use the reduction formula again, given in the integration by parts section. And what do I mean by this? I mean the following. You can express the integral of sine to power 4x in terms of the integral of sine squared x, right? So this is, one application of the reduction formula allows you to go 2 levels, right? Reduce the degree by 2. So you can connect sine to power 4x with sine to power 2x, and you've already done the work for sine to power 2x, right? So you can extract information from this work to actually complete the work of that integral. Okay, so this would be approach number 1. And approach number 2. So approach number 2. So complete this on your own, okay? But again, if you're stuck at any stage, consult with me, and I'll be very happy to help you. So approach number 2. We're gonna also, we're gonna do the same strategy that we followed in example 3, and that strategy was applying one of the half angle identities, right? So it's gonna be the same. So here we're gonna apply half angle identities. That were mentioned above, right? Okay. So I'm gonna rewrite sine to power 4x. I'm gonna use asterisk. Sine to power 4x is the square of sine to power 2x, right? So sine to power 4x can be thought of as the square of sine to power 2x. The square of the square is that thing to power 4. And this is the square then of what's sine squared theta or what's sine squared x in terms of cosine by just linearizing the power. So what I'm saying is use the half angle identity above, which was labeled as asterisk. And what is that? What do we get? Well, it was 1/2 1 minus cosine of 2x, right? This is what asterisk was. And then what do we obtain? you square this entity, so this becomes 1/4 of the square of this guy, correct? And how do you square a difference? You square, let's say, the first one, so 1 squared is 1, minus twice the product, so minus twice cosine 2x, plus the square of cosine 2x, correct? So we get this. So sine to power 4x is at the end of the day this guy, okay? So the primitive of sine to power 4x is going to be the primitive of 1/4 times 1, which is easy. That's going to be the primitive of 1/4 times 2 times cosine of 2x. So it comes down to finding the primitive of cosine of 2x, which is also easy. We've done it, actually. It's right there, right? It's very similar to this work that was actually done in example 3. And the last part, we're going to integrate cosine squared of 2x. So in order to integrate cosine squared of 2x, this is very much like integrating sine squared. And what did we do at the time? We also applied the half angle identity. So now we're going to apply the half angle identity, but the second one, because we're going to have cosine squared theta. So how about giving it the name double asterisk? This identity is labeled as double asterisk. I'm gonna use that to integrate cosine squared 2x. Okay, so let's put things together, and then I continue by using double asterisk. So then primitive of sine to power 4x dx is simply 1/4 primitive of 1 minus 2 cosine 2x plus cosine squared 2x dx, which is equal to 1/4. Let's keep it in factor, right? It's a multiplicative constant, so it's in factor for everything. Primitive of 1 dx, which, as I previously said, easy, minus 2 primitive of cosine of 2x, that's dx. That's also not as easy as this, but it's quasi easy. Actually, we've done it above, as previously said. And finally, plus the integral of cosine squared 2x dx. Okay, and as promised, I'm gonna make use of double asterisk above. So I'm gonna use double asterisk above the double angle, the half angle formula, to rewrite cosine squared theta. What was cosine squared theta is equal to so cosine squared theta is equal to half the sum of 1 plus cosine of 2 theta, right? And again, the essence here is we are linearizing the power. Instead of having power 2, we're gonna be down to power 1, right? So we're gonna increase the angle. The angle is not gonna be the same from theta to 2 theta, but the power is gonna be reduced, right? So that's the essence of this identity, or those two identities above. So we get half times 1 plus cosine of 2 theta, right? That's my theta in my context. That's my theta. So let me color it in something else. How about in red? Okay. So that's my theta. The red part is my theta. Let's keep it red here. So twice the red part, which is the theta. Make sense? One more time. The formula, the half angle formula, double asterisk, reads as follows: cosine squared theta is equal to half times the sum of 1 and cosine of twice theta. My theta happens to be 2x here, so instead of theta I'm writing 2x. Okay, and this becomes half times 1 plus cosine. What's 2 times 2x is 4x. Okay, and we can integrate this easily. One of them is very close to this and the other is very close to this. Okay, so let's keep going then. That's then equal to 1/4 this guy, and this guy is x, minus 2 times this integral which was found above. How much was it? What did we find? We found it was half primitive of cosine, which is sine of u, right? So it's gonna be half sine of u. So the intermediate step actually, let's complete the intermediate step here. So the intermediate step actually is, before I evaluated it, so it was half the primitive of cosine, which is sine of u, right? And that was taken between 0 and 2 pi at the time. So that's the primitive, up to taking the constant to be 0. Let's take the constant to be 0, and the a primitive of cosine u is half, or half cosine u is half sine u, right? And what was u? U is 2x. So what I'm gonna write below is gonna be half sine of the 2x. Okay. Okay. So this is half of sine of 2x, and I'm gonna tell you here, just see above. See discussion above. So on previous page. Okay. And by previous page I mean just the one that we were just talking about. Alright, so back to this. This becomes 2 times half times sine twice x, okay, plus the primitive of half. So the primitive of half times 1, so half dx, plus the primitive of half cosine 4x, right? So let's put the half outside. Cosine 4x dx. 4x dx. Okay? So one more time, what did I do? This guy is this. This guy is this. And now the pink guy is technically just this part, right? That's the pink guy. So the primitive of the pink is going to be primitive of half dx plus primitive of half cosine 4x dx. Okay? Alright, one of them is immediate. This one, let's say. And what is that? This is half x. Correct? Again, let's forget about the constant for the moment, just combine the integration constant at the end. Call it one arbitrary constant, let's say c. Okay, and now how do we do this one? Guess what? We're gonna play the same game as we did over here. Correct? Now we have 4 instead of 2. So that's gonna be 4, that's gonna be 4, that's gonna be 4. The same treatment, right? And this is gonna be 4, etc. So that's gonna be 4 sine u, and u is 4x. Correct? So what's gonna happen is the integral that we have, the indefinite integral that we have below, which is primitive of cosine 4x dx, is gonna be simply 1/4 sine of 4x. Make sense? It's the same treatment. Try it on your own if you're not happy with this explanation. Alright, so let's keep in mind it's 1/4 sine 4x. So 1/4 sine 4x, right? So technically it's the same discussion that's gonna be applied here. Okay. Let me just put exclamation mark just to tell you that I explained this at least in the video, okay, if you see it in the notes. Alright, so therefore this is equal to 1/4 times x minus 2 divided by, so 2 times 1/2 is 1, so sine of 2x, this entity, plus half x plus 1/2 times this integral, which is itself has its own multiplicative constant 1/4. So 1/2 times 1/4 is 1/2 times 4, which is 8, sine of 4x. And as I promised, now I'm gonna add that arbitrary real number c, the constant of integration. Okay, so where c is an arbitrary real number. Okay, chosen. Okay, all right, so this would be the integral of, obviously you can combine half x with x, right? X plus half x is 3/2 x. All right, you know what, let me do it. So this is equal to 1/4. As we said, x plus half x is 3/2x minus sine of twice x plus 1/8 sine of 4x plus that c, right? So plus that c, so technically the comma is here. Okay, very good. So try to actually convince yourself that in approach number 1, by using the reduction formula, you get exactly that primitive function. Okay, so 1/4 of that sum plus a constant. To summarize our strategies that we found along the way, let's go to the book on page 532, and the guidelines for evaluating integrals that similar to the ones we just discussed are given in this table. So let's actually take it as a picture and paste it in the notes. Okay, so let's leave it here. So this would be the guidelines to integrate integrals of the form sine mx cosine nx, right? Depending on the power. If the sine has an odd power, we reserve one of the sine factors by itself, and then we use the Pythagorean identity to actually write the even power of sine in terms of cosine, and then we use the substitution u equals cosine. Okay, so this is like example 2 in the discussion above. Guideline number 2, if the cosine has an odd power, then we reserve one of the cosine by itself, and then the remaining one we use the Pythagorean identity to write cosine squared in terms of sine squared, and then we use what u equals sine x as a substitution. And this would be like example 1 above, right? Now, if both of them occur, in other words, if both powers of sine and cosine are odd, you may use either 1 or 2. Okay, you may use any of the two. And now, if both of the powers are even, as we saw above, we use the half angle identities labeled here. We call them asterisk and double asterisk in discussion. Okay. All right. So the same process can also be applicable if we want to integrate functions that look like tangent of mx sec nx dx. Because the derivative, for example, the derivative of, if you differentiate tangent of x, you obtain secant squared, right? So the derivative of tangent is secant squared, which means if this n is even, if this n is an even number, then you can save two copies of sec by themselves, right? So you put sec squared by itself, and then you label u to be tangent, and you also use a relation between secant and tangent. If this is even and you chip away 2 units, that remaining power is going to be n minus 2, which is also going to be even, and you may use this relationship between tangent and sec. So sec squared x is equal to 1 plus tangent square x, right? So because of these two properties, you may say also if n is even for the power of sec, then you can reserve a couple of copies of secant, and you can label u as tangent and apply this relationship between secant and tangent. We're going to see it in an example. On the other hand, we know that the derivative of secant of x is sec tangent, right? Sec x tangent x. And we can manipulate this and rewrite tangent squared x as secant squared minus 1, correct? So these two properties allow us to say the following. If this guy m is odd, and odd can be written as 2k plus 1, where k is an integer, right? So if m is odd, then you can do the following. You can take one of the tangent factors. So if you take one of the tangent factors, you're going to be left with an even number as a power for tangent. So you're going to isolate this one by itself, right? So tangent to power 2k plus 1 can be written as tangent to power 2k x times 2 times tangent x, because you add the powers, right? This is power 1 here. We don't typically write it. And what you can do is you can, if n is not 0, you can leave one of the n by one of the copies sec that you have and combine it with the tangent. So you're going to be left with secant to power n minus 1 together, and one of the copies of sec accompany the tangent. And why this becomes useful? Because of these two properties then. Remember, tangent to power 2kx is the same as saying tangent to power 2, and the whole thing is to power k, right? You can write it like this. And then now, because of these two properties, you can say, okay, if you write u to be secant, right? If you write u to be secant, tangent squared becomes u squared minus 1. So tangent squared becomes u squared minus 1. This becomes u to power n minus 1, and this becomes du, right? Because secant is u, so this becomes du, and then you are integrating a polynomial. Okay, so we're back to a situation similar to the ones we discussed above. Okay, so the trick that was used in integrating functions that look like product between powers of sine and power of cosine can be carried out to actually at the level of tangent and sec, and the idea is, because here the relation between sine and cosine is at the level of the Pythagorean identity and at the level of derivatives. Similarly, we have similar properties here between sec and tangent. So whenever any of these two situations occur, we're gonna apply the appropriate substitution. Okay, so let's start by the first one. Let's see it in action. So let's consider, so that's example 5. So let's consider the following integral. The primitive of tangent to power 6x secant to power 4x dx. Okay, so this is, keep in mind those two properties in the first bullet. So I have an even power of sec. So what I can do is I can rewrite this as secant squared x times secant squared x. So I'm reserving 2 copies of secant. I'm setting the stage for secant squared dx, secant squared x dx to look like d tangent, right? And the other secant squared, this guy, I'm gonna use 1 plus tangent squared to replace it. And then I'm gonna use the substitution u to be tangent. Okay, so concretely, this is what I'm saying. I'm saying that this is equal to primitive of tangent to power 6 x times secant squared x times secant squared x dx. And don't forget that this guy here, secant squared, right? Secant squared is 1 plus tan squared. So secant squared x is 1 plus tangent squared x. And as such, this becomes the primitive of tangent to power 6x times 1 plus tangent to power 2x times secant squared x dx. I hope you see the similarity between integrating a product of trig functions. Each one of them looks like power of either tangent or sec. I hope you see the similarity with the other one, which was discussed above when we were integrating sine against cosine, power of sine against power of cosine. Okay. All right. And as before, what did we do? So let's let us set u to be tangent of x, and then du becomes sec squared x dx, right? This is what we said above. Okay. So then this becomes primitive of tangent x to power 6 becomes u to power 6 times 1 plus tangent squared becomes u squared, and this entity here, sec squared dx, is the du, right? So sec squared x, that's the sec squared x guy, and that's the du, correct? So that's du. And we're back to integrating a polynomial. That's easy. So this is equal to u to power 6 plus u to power 6 times u to power 2 is u to power 8, right? Du. So that's 1/7 u to power 7 plus 1/9 u to power 9 plus a constant of integration. And now let's go back to replace what u means to us. It means simply tangent of x. So that's equal then to 1/7 tangent power 7 x dx, x plus 1/9 tangent to power 9x plus c, where again c is an arbitrary constant. So where c is arbitrary. Okay. So now let's consider a situation where takes care of the second bullet. So in other words, where the power of tangent is odd. So let's call this example 6. Okay, so let's find the primitive of tangent to power 5 theta secant to power 7 theta d theta. Okay, so now the power of tangent is odd, and as we discussed above, we're gonna separate one of those copies of tangent and separate one of the sec factors, combine the two, because in concert with using this identity here, if you set u to be secant, you're going to be able at the end of the day to find a polynomial, and this whole thing becomes a du. Okay, so let's do that. So as we said, we're going to take one copy of tangent and one copy of secant to get tangent x secant x dx. And what I'm gonna do here, as we discussed above, I can rewrite tangent to power 4 as the square, right? As the square of tangent squared of theta times secant 6 theta times this guy, so tangent x secant x dx, right? And tangent squared theta, as discussed above, this is the same as secant squared theta minus 1, correct? So that's secant squared theta minus 1, and as such, if you introduce the letter, the letter u to be secant of theta, that forces du to be secant theta tangent theta, right? D theta, correct? So this is the du then, right? This is the du as previously said. This becomes u to power 6, and this becomes the square of u squared minus 1, correct? So let's do that. This is then equal to primitive of the square of, right, the purple guy is that guy inside, the square, that's the square, sec squared theta is u squared minus 1. Okay, so one more time, secant theta is u, that thing becomes u squared minus 1, and the whole thing is squared, times secant is u again, so this is u to power 6, times that whole thing is du, as we said, right? This whole thing is du, correct? I'm sorry, here I meant, okay, my bad, I've been writing x instead of theta. So all these are theta, my bad, right? So theta, theta, everywhere. Okay, so we get to this point, and what? So now we're integrating a polynomial as promised. Let's do it. So squaring a difference, once again, this is the square of the first, so u to power 4 minus twice the product, so 2 times u2 plus 1, right? 1 squared is 1, times u6 du. Okay, and this is simply the primitive of, now we're gonna distribute the multiplication over subtraction and addition. We're gonna get u to power 4 times u to power 6 is u to power 10 minus 2 times u to power 2 times u6 is u8 plus u6 du. Okay, and this is 1 over 11 u to power 11 minus 2 over 9 u to power 9 plus 1/7 u to power 7 plus a constant of integration, And the final step obviously is to rewrite what u means to the problem. It's simply sec of theta. So that becomes 1 over 11 sec to power 11 theta minus 2 over 9 secant to power 9 theta plus 1 over 7 secant to power 7 theta plus c, where the c is an arbitrary constant. Okay. So we discussed above the situations when we have primitive of factors, each of which looks either power of tangent or power of secant, right? So technically we're talking about this, and we said if the power of secant is even, then we did an example like that. This was example 5. And when the power of tangent is odd, we did an example like that, which was in example 6, right? So for the other guidelines, for the other cases, the guidelines are not as clear-cut. So we may need to use sometimes identities, integration by parts, and sometimes we have to be innovative. Okay? So occasionally we will have to make use of a couple of formulas. So one has to do with the integral of tangent, and this was discussed in Calc 1, right? So this was discussed in the video entitled Logarithmic, Exponential, and Transcendental Function. Which has to do with differentiation and integration of these type of functions. And this is ln of absolute value of secant x, or we also found it to be negative ln of absolute value of cosine, right? So they're the same. The other one is the primitive of secant. So we haven't discussed this. Let's actually discuss it. Let's prove it in different color. How about pink? Remember, secant is 1 over cosine. So I can rewrite this as secant x times, I'm going to multiply it by number 1. And this one is going to look like sec x plus tan x divided by sec x plus tan x. Okay? So this is a 1 here. So this is a 1, right? This quotient is a 1. dx. So you may think, okay, what if sec x plus tan x equals 0? Is it possible to have sec x? So is it possible? Is it possible to have, because look, I'm multiplying and dividing by this entity. What if this guy sec x plus tan x equals 0? Right? If it's 0, this is nonsense. We cannot do that. So is it possible to have this equals 0? Keep in mind that if they're asking to integrate sec x, they are already implying that this is meaningful, right? And secant is 1 over cosine. So this already entails, this question already entails that secant is meaningful. And secant being meaningful, this means that cosine is not 0, because secant is 1 over cosine, right? If you say that secant exists, you're saying that cosine is not 0, the denominator is not 0, correct? Which means x cannot be 3 pi over 2. It's not equivalent. It implies, I'm going to just use it this way, x cannot be 3 pi over 2 plus 2k pi. Am I correct? Where k is in z. You agree with me? So what I'm saying is, asking to integrate this, they already there's a provision here. The provision is that this guy exists. And for this to be meaningful, you're asking that cosine is not 0. And for cosine not to be 0, it means that it's neither pi over 2 plus 2k pi nor 3 pi over 2 plus 2k pi. Okay? So I'm going to just say that for sure if this is the case, then this is going to happen, right? Okay? Now, back to this green question. What happens if secant x plus tan x is 0? What does this mean? Well, this question then is equivalent to saying 1 over cosine, which is secant, right? Secant is 1 over cosine, plus tangent, which is sine over cosine, is equal to 0, which is the same as saying that we have the same denominator here, cosine x. So 1 plus sine x divided by cosine x is equal to 0. So asking this question is the same as asking this question, which is the same as asking this question. So now can this happen? Well, keep in mind, cosine is not 0, right? So cosine is not 0. And if cosine is not 0, x is not any of these points, right? It's not 3 pi over 2 plus 2k pi for any k in z, for any integer k, right? So since x cannot be as such, this means that this numerator cannot be 0. Does make sense? Because the only time 1 plus sine x is equal to 0 is when sine is equal to negative 1, and sine is equal to negative 1 happens precisely when x is 3 pi over 2 plus 2k pi for some k in z. Since x is none of those points, the 1 plus sine x is not 0, and as such this quotient is not 0, and hence this sum is not 0, and therefore this is meaningful. Okay? So I just wanted to discuss this to let you know that what I'm doing here is meaningful. Anyway, so this is a side here, right? Let's keep going with the pink discussion. So that's equal to, let's color this pink actually. So that's equal to what? Primitive. So the denominator is sec plus tan, sec x plus tangent x dx. And upstairs, what do we have? We have sec times sec, so sec squared x plus sec x tan x, right? Okay. And what I'm gonna do now is I'm gonna go for a substitution. I'm gonna go for the following substitution. I'm gonna let let's say t to be sec x plus tan x. Okay. What's dt then? What's dt? It would be the derivative of secant, which is sec tan, right? And the derivative of plus the derivative of tangent, which is secant squared, secant squared x dx, right? So we get that. And then this integral becomes, so downstairs that's t, and upstairs, take a look. Upstairs we have secant squared x plus secant x tan x dx. So we have all of dt. We have all of dt, right? So what I'm saying is what you see over here is simply dt, right? Okay. Excellent. So this is then, this is then equal to what's the primitive of dt over t? So this is ln of the absolute value of t, right? Plus a constant of integration. And what's t? T is secant x plus tan x. Right? So this is equal to ln of absolute value of secant x plus tan x plus a constant of integration. Okay, so we may say then we may say then a primitive of secant is simply ln of sec x plus 10x, right? And if you add a constant, you're covering all those antiderivatives. Okay, so keep these two results in mind, this bullet and that bullet, and we're gonna see them popping up in the next examples. So let's consider example 7, and let's evaluate the integral of tangent cube x dx. Okay, so here we only have tangent, we don't have sec, but we know this relationship between sec and tan, right? We know that. So what do we know? Let me write it in brown here. So we know that tangent squared x is equal to secant squared x minus 1, right? So we know this thing, so recall it. It was mentioned above. Okay. So to set the stage, let's isolate that guy, tangent squared, from tangent cube. We get tangent, oops, let me keep it in purple. So we get tangent x times tangent squared x, which is tangent x times sec squared minus 1, right? So sec squared x minus 1. So what I used technically is this part, right? I used it right there. Okay. So I used this guy over here. Very good. So then this integral then is equal to this integral is equal, how about we give it a name j. So j is equal to the integral of tan x times secant squared x minus 1 dx. And what I can do is I can distribute the multiplication over subtraction to obtain tangent x times secant squared x minus tangent x dx. Correct? Do we know how to integrate tan times secant squared? Yeah, it's simple U substitution. You can so here the power of secant is even, right? So if you call u to be secant, as we did above, if you call u to be secant, then the derivative of secant is going to be sec tan, right? So you can play it this way. Or similarly, you can use u to be tangent, and the derivative of tangent is secant squared. Okay, so any of the two alternatives that I just mentioned work for the first one, and the primitive of tangent for the second entity, we've just discussed it, right? We've just discussed it above. It's this guy. Okay, so let's write the details. So this is equal to primitive of tangent x times secant squared x dx minus the primitive of tangent x dx. This was just recalled above. This one. This is, let's say, ln of absolute value of secant, which is also minus ln of cosine of x. For this part, there are two ways to do it, or at least I can see it in two ways. One way is, how are we going to do this? How about, so one way, I can write this as tan x times sec x, okay, oops, times secant, right? So this is the same as secant squared tangent, so the same, times dx, right? And all this thing is d of that, right? The differential of secant, because the derivative of secant is sec10. So this becomes then equals to, if you call u to be secant x, then du becomes sec x tan x dx, right? So we get this. Okay, so this is u du then. This whole thing is du. And this is u squared over 2 plus a constant. Let's add the constant at the end of the day. So u2 over 2, and u is secant. So this is secant squared x over 2. Correct? So secant squared x over 2. Alright, so and then we get equal, right? This whole thing becomes equal to this this purple one. So secant squared x over 2 plus or minus the green one, which is ln of absolute value of secant x plus some constant of integration. Correct? So this would be the primitive of tangent cube. In other words, if you differentiate this, you're going to get tangent cube. Now, I told you that we can do this guy also in a different way, right? So let's do it. Let's use this color. How about we give it a name? So actually, let's call this first way. So first way. So this is a first way, or our first way to do this. And now if you wanna do this in a different way, let me call it 3 dots here. So, and let's continue it here. So that would be the second way. Okay. So what do we have? We have this guy, the integral of tan secant squared. So the integral of tan x secant squared x dx minus the primitive of tangent x dx. That's what we had above, right? That's what triple dots are. Okay. All right, and I told you that you can actually set u to be tangent. So set u to be tangent of x, and as such du becomes secant squared x dx. Okay, and this is then equal to the primitive, that's u, and that's du, right? That's du minus primitive of tan x dx. Okay, did we call this u above? Okay, since we called this u above, how about I change the name of this variable? How about w instead of u? Okay, so how about w? So this becomes dw, and that guy becomes w dw. Okay. All right, so this is then equal to, what is this? This is w squared over 2, right? Minus the integral of tan, and the integral of tan we discussed it above. It's ln of secant, absolute value of secant of x, plus some constant of integration k, right? So this is then equal to w squared over 2, which means tangent squared x over 2 minus ln of secant x plus k, and keep in mind that k is an arbitrary number, constant in R. Correct? And above, that c also was arbitrary in R. So where c is a real number, that's arbitrary. Correct? So these are two ways to do that same thing, and apparently I got two different answers, right? So apparently I got two different answers. Let's highlight those answers. For the first one, I got this answer, and for the second one, I got this one, and they look different. They look different. Take a moment to convince yourself that they are actually the same. And the way I'm going to explain it to you is, I'm going to go from the pink one to the blue one. Right? So how about we label them? Actually, so I'm going to ask, why are the two expressions, or the two answers above, by answers I mean antiderivatives, so why are they the same? So why are they identical? Okay, so, well, tangent squared x over 2, this guy, minus ln of secant x in absolute value plus k is equal to tangent square x is the same as, what's tangent square in terms of secant? Tangent square x is equal to secant squared minus 1, right? So this guy is secant squared minus 1. So you can write secant squared minus 1, secant squared x minus 1, over 2 minus ln of the absolute value of secant x plus the k. Correct? And that means this is equal to secant squared x over 2 minus 1/2, I'm splitting this quotient, minus ln of absolute value of secant x plus k, right? And that's the same as secant squared x over 2 minus ln of absolute value of secant x plus k minus half. Am I correct? I just moved the half to the end. Okay, and now let's zoom out and compare the two answers. So technically I'm gonna compare I wanted to compare these two, right? I wanted to make the case that these two are the same. Well, this in turn happened to be this. This, right? Oops. Just a second. So happened to be this one, right? So this guy happened to be this guy. So what can we say then? What can we say? The question becomes, are these the same, right? This guy and the box, are they the same? Well, they look very close except for this guy here at the end, right? So this looks like the C. So that C, which is arbitrary, and the K, which is arbitrary, correct, have a relationship between each other. The C is actually K minus half. Since K is arbitrary, C becomes arbitrary. Make sense? So the two expressions are identical because the constants are arbitrary. If the constants are not arbitrary, they're not identical. But since k and c are allowed to be anything, then these two expressions are the same. And technically, the relationship between c and k is as follows. C is equal to k minus half. Okay? In other words, also k is equal to c plus half. Okay? Alright, so that's the c then. That's the c. Okay? And as such, they are the same. Let's do now a problem that has to do with powers of sec. Let's call it example 8. So powers of sec may require integration by parts. So let's say I want to evaluate the indefinite integral sec cube of x dx. Okay. So that thing is the same as, if you call it I. So I is the same as primitive of secant x times secant squared x dx. And I'm gonna use integration by parts. Typically powers of sec require by itself. If sec exists by itself, typically this requires integration by parts. And if you use integration by parts here, so use IBP with the u prime to be secant squared x and the v to be secant x. Okay, so as such, u is tangent x and v prime is secant x tangent x. Correct? So let's see what this leads us to do. Then I becomes a uv, right? uv, so sec x tan x minus the primitive of uv prime. So uv prime is sec x tangent squared x, right? So sec x times tangent squared x dx. Okay. Alright, so now I'm gonna relate tangent squared as above. I'm gonna relate tangent squared to secant squared. Tangent squared is secant squared minus 1, right? So tangent squared is secant squared minus 1. And then this blue part becomes equal to secant of x tangent of x minus the primitive of secant x times secant squared x minus 1 dx. Okay, and let's multiply now. Let's distribute the multiplication over subtraction to obtain secant x tangent x minus the primitive of secant cube x minus secant of x dx, right? So we found the primitive of secant cube x dx, which is what? Which is I. This is I. So we found it along the way, so with a minus sign. So therefore, right, therefore all this is equal to I. All this thing was equal to I. So therefore I, I'm just copying I, is equal to secant x tangent x minus, right, minus, again, the primitive of secant cube dx, that's the I. That's the guy I, plus the primitive of secant x dx. So one more time, primitive of secant cube x dx, that's the I guy. Okay, so I'm replacing, instead of writing primitive of secant cube dx, that's the I, and minus times the minus is plus the primitive of secant x dx. We know the answer of this, right? We just discussed it above. That guy is equal to we found ln of the absolute value of secant x plus 10x. Okay, and let's keep the constant of integration till the end. So we solve for I as usual, right? We solve for I. Let me actually add the constant, that's fine. So we solve for I. What do we get then? Add I to both sides, you get twice I equals secant x tangent x plus ln of the absolute value of secant of x plus tangent of x plus c. Keep in mind c is an arbitrary constant, and this means that I is half of twice I, so I is half of that. So it's gonna be half of secant x tangent x plus ln of the absolute value of secant x plus tan x plus half c plus half c. I'm gonna call it k, right? You can, alright, let's just keep it half c. And now, since c was arbitrary and in R, right? So since c was arbitrary in R, k is gonna also be arbitrary in R. So where c was arbitrary in R. So now if you rewrite half c to be k, then you get I is half secant x tan x plus ln of the absolute value of secant x plus tan x plus that arbitrary constant k, right? Because c was arbitrary, half c is still arbitrary. So where k is an arbitrary real number. Okay. These guidelines that we just discussed are on page 535 in this big table. So I'm gonna include it as a picture in the notes. So let's paste it here. Okay. All right. So you may read it, and keep in mind that integrals of the form, so this is like a note here. So integrals of the form cotangent to power mx times cosecant to power nx can be found, in similar methods, so similar approaches as we just discussed for tan to power m times sec to power n, and this is because of the identities. So what do we know? We know that 1 plus cotangent squared x is equal to cosecant squared x, right? We also know that if we differentiate cotangent of x, we obtain minus cosecant squared of x. And if we differentiate cosecant, we obtain minus cosecant x cotangent of x, right? So these are very reminiscent to the properties that hold between tangent and cotangent, and whatever we whatever guidelines we have for tan secant, we can run them for cotangent cosecant. Okay, because of the nature of the properties that link those two functions together. All right. So finally, if we wanna, let me change the color. So finally, if we want to evaluate integrals of the form sine mx times cosine nx. So here we don't have the power m that used to be power. Now it's a multiple for the angle, right? The x. So if we want to evaluate integrals of this form, so cosine nx or mx, doesn't matter, cosine nx dx, or primitive of sine mx times sine nx. So any of these forms, we appeal to trig identities that are in the book. So let's go there. They come from the trig course, and I'm alluding to these particular ones. Okay, so let's also take it as a picture and paste it here. So this relates sine mx times sine nx in terms of cosine, difference of cosines, and sine mx times cosine nx in terms of sine, and cosine mx times cosine of nx in terms of cosine. So these are what you used to call product to sum identities, right? Let's take an example. So this is example 9. Okay, so find the integral of sine 3x cosine of 6x dx. All right. Sure, we can use integration by parts here to actually evaluate this, but it would be much easier to use one of these properties that are mentioned in this box here, right? Namely, I'm talking about this guy, okay? Because this is of the form product of sine mx times cosine nx. So let's give this guy a name. How about we call it 2, right? So by 2 above, we may write that sine 3x times cosine 6x is equal to 1/2. So the m is 3 and the n is 6. So this becomes, again, this is 3 and this is 6. So this becomes 3 minus 6, which is minus 3. So sine minus 3x plus sine of 9x, right? So sine of 9x. And this would be the integrand. Okay? So this integral, let's give it a name. How about a? So thus a is equal to half. So the integrand now is this purple thing, half primitive of sine of negative 3x dx plus the primitive of sine of 9x dx. Correct? And what's the primitive of sine alpha x dx? Let's do this on the side. So let's do this on the side. What is primitive of sine alpha x dx? Obviously we're gonna use u substitution. So we're gonna call u to be alpha x. Let's suppose alpha is not 0. Right? Let's suppose alpha is not 0 along this discussion. So u is equal to alpha x. That means du is equal to alpha dx, which means dx is alpha inverse, or 1 over alpha du, right? So then this becomes equal to a primitive. Again, I'm supposing alpha not to be 0, because if alpha is 0, this whole thing is 0, so it becomes easy. But I'm dividing by alpha, so I need that guy not to be 0. And this becomes the primitive of sine of u, right? dx is 1 over alpha du. So let me make room for 1 over alpha to be pulled outside. 1 over alpha du. Correct? And this is 1 over alpha. Primitive of sine u du is negative cosine u plus a constant, right? Agree with that? So this is then equal to 1 over alpha times negative 1 times negative 1 cosine of u, and u is alpha x, plus a constant, correct? Let's just erase the constant and combine all the constants at the end of the day. Okay? Alright, so this is the discussion I want to invoke a couple of times. One time when alpha is minus 3 and one time when alpha is 9, correct? So we're gonna use this discussion. Let's give it a name. How about discussion lambda? Let's call it capital lambda. And this is equal to so that's equal to by lambda, by discussion lambda, this is equal to 1 over 2. Again, I'm gonna use lambda one time when alpha is minus 3 and one time when alpha is 9, right? When alpha is minus 3, this becomes minus 1 over negative 3 cosine of minus 3 alpha, correct? I'm reading this when alpha is minus 3, plus this guy when alpha is 9 now. So I'm going to have minus 1 over 9 cosine of 9 alpha, of 9x, right? And plus c at the end of the day. Alright, so maybe I need to be clear in the notes. So I'm making use of this twice, right? One time alpha is gonna be minus 3 and one time alpha is gonna be 9. Alright, so I'm explaining what happened here. So one time alpha is minus 3, one time alpha is 9, and those are the results, right? So then this is equal to 1/2 times, this is 1/3 cosine of negative 3 alpha. What do we know about the function cosine? It's an even function, right? Cosine is an even function. So cosine of minus 3x is simply cosine of 3x. This is x here. This is x, right? So that's x here. Then we get cosine of 3x because cosine is an even function, right? Is an even function. Correct? Which means cosine of negative theta is equal to cosine of theta. Okay? Alright, so then this is equal to cosine of 3x minus the 1/9 cosine of 9x plus the c. Again, as usual, where c is an arbitrary real number. Okay. Alright, so this completes this section, which was about trig integrals.